Hello everyone. Uh, Welcome to TL Eliminators, Codeforces post-contest discussion. This is the post-contest discussion for round 1026 Div 2 contest on Codeforces. And today we'll be covering problems A to D. Just quickly before we start, can someone confirm that I'm audible? Can someone quickly confirm in the chat? Can someone confirm if I'm audible, please? Just drop a message in the chat. I'm audible, everyone? I can see 23 people watching, so if you quickly just confirm if I'm audible. All right, I'm going to assume that I'm audible because I'm not getting any response from the chat today. I do not know why, but okay. Um, let's begin. Before we begin, yes, I want to, remind you that, or if you're new here, that TLE Eliminators, I'm Vibhaas Srivastava from TLE Eliminators, and today we're going to discuss round 1026 in Div 2 in Codeforces. And that TLE Eliminators has, courses for practicing CP specifically. Like, for example, if you got stuck at one or two problems, or, you know, really struggle to solve the problems in today's Div 2, then TLE Eliminators is currently running self-paced courses, which provide you with video lectures, practice problems, and then guided hints to each practice problem. Each practice problem has a video solution, and we have dedicated doubt support where mentors such as me and other high-rated mentors are available almost 24/7 to answer your doubts. Then also we have a gamified platform, with a whole leaderboard and things like that to encourage you to, keep up with CP. So if you feel lonely in your CP journey, or if you feel your CP journey isn't going well enough, then you can come join us at TL Eliminators and we'll be glad to help you out. All right. Okay, yeah, I don't know why the chat is not was not showing for a while, but okay, let's see. The chat is working. Is there a delay in the video? Is there a delay in the video? Please confirm. Is there any lag in the video? I'll try to fix it if that's the case. But yeah, okay. So we'll start as usual with problem A, and then we'll do A, B, C, D in order. So problem A this time was, I think, fairly simple. So let's not, like last time I got some comments that I spent too long on A. Uh, so I won't waste too much time and people want me to start, but okay. So what do we have to do here? We have to make sure that given an array of integers A, it is fashionable if min of A plus max of A is divisible by 2 without a remainder. What does that mean? It means that given an array A1 to AN, if the sum of minimum of A1 and maximum of like the sum of minimum of this array and maximum of this array, if this is even, that is divisible by 2, if it is even, then uh, then we can say that it's fashionable. And now, if the array is not fashionable, what we can do here is the question says we can remove any element from this array. Our task is to determine the minimum number of operations required to make array A fashionable. All right. So the question is very straightforward. We need to make sure that for this array, min of array A plus max of array A, this quantity is even, right? So this is the thing we care about. And let's just quickly check what the constraints are. So n is only till 50. So, we don't really need to worry about n. It's the first problem. So the constraints don't really matter that much. Okay. So how do we approach this problem? Well, first thing we can say is since we are only dealing with minimums and maximums, and we are also removing elements from the array, our best idea will be to sort this array. So we can write um, observation one, sort the array. And we can see that sorting the array does not change the answer because even if it's a sorted array, unsorted array, whatever order, minimum or maximum does not change. So just to simplify, let us sort the array in ascending order. So then A1 will be the smallest element and uh, AN will be the largest element. So what does our condition become now? What does our condition for fashionable condition? What does that become now? That condition can now simply be written as A1 condition, we'll write it in, let's say, blue. And our required condition is A1 plus AN is even. So this is the condition we need to satisfy. All right. Basically, if the array is sorted, we can say that first element plus last element must be even. And that's what they want here. Min of A plus max of A should be even. Now, what if it is all, look, if it's already even in the start, then we can just print zero because zero operations are required and that's it, we're done. But what if it is, what if it's odd? So we can see that if it will only be odd, A1 plus AN will only be odd if one is even and one is odd. So one of these two is even, one is even, and one is odd. So that means they are both of opposite parity, right? And then only then will A1 plus AN be odd. So how can we fix this? Let's check. One approach can be, we need to, obviously, if we do an operation and the minimum and maximum does not change, that means we are wasting the operations. So basically in every operation, the minimum or maximum has to change. Otherwise, that it's like a waste of an operation, like in a greedy sense. So let's say we have this array and let's say this one was even and this one was odd. And this is in sorted order, by the way. So this does not satisfy the condition. So, okay, so what if we delete the first element? Then we go to the next one. And if this is even again, then we can delete the minimum element again. And then finally, maybe this one is odd. So now these two's parity match. These two's parity match. And we can say that we have satisfied our condition. So this is one way of doing it. The other way of doing it, instead of deleting minimums each time, what we can do is we can delete the maximums each time. So we're lowering the maximum instead. And again, let's say this is even and this is odd, and this is odd. Then let's assume that this is also odd, this is also odd, this is also, and this is even. Okay, so it's the same example from last time. Yeah, so here what we can do is we can delete this, but still it's odd plus even, which we don't want. So again, we delete this. Again, it's odd plus even. We delete this. Now it is even plus even, and it is satisfied. So how many moves did it take here? Number of moves is 3 moves. And how many moves did it take here? The number of moves is 2 moves. So now in these two, we can show that our answer will always be the minimum of these two cases. Min of these two cases. And so we'll just take min of these two cases, and that will be our answer. So we can call this, I guess, observation 2. observation 2 for this problem. And that's all. The problem is solved. Now we need to write some code which checks which one, which checks like if they're of opposite parity, if the smallest element and largest element are opposite parity, hello. Yeah, it was. I heard comments that it was lagging. So sorry about that. Um, can you see my screen now? And I think it should not be lagging. Can you do questions C and D first from next contest onwards? All right, I'll consider it. But a lot of people want B also today, I think. But yeah, okay. Now I think it should be fine. Yeah, is it fine? All right. Okay, so I hope nothing too much was missed, but I'll just recover it quickly. Okay, so we sort the array and we need to check if first element plus last element is even or not. If it is not even, that means one is even and one is odd. And we need to get them both to the same parity. So in this case, we can do one thing. We can delete elements from the start until they're both same parity, or we can delete elements from the end until they're both same parity. And in this case, we see how many moves it takes. And in this case, we see how many moves it takes. And we take minimum of that. Okay. So this was A. I guess most people would have done A, but yeah. Um, so because I was also in a hurry in the contest, my code isn't that clean, but I'll show it to you anyways. Um, so first we take in our array A, we sort the array. So we can write that in the steps. Solution sort array, or we'll just write one sort array. And we can say that, so what I'm doing here is first and last. These are the first points that my parity of my elements changes. And last FL is my last point such that my parity of my element changes. And why am I doing this? I'm doing this because in case, in case that A of 1 plus A of n is even, in that case, we can simply print 0. Else, what I'm doing is I'm finding first point parity changes first A of I such that parity of A of I, parity means evenness or oddness, parity of A of I is not equal to parity of A of 0. So the first point such that if the first element was odd, then I'm trying to find the first even number. And if the first element was even, I'm trying to find the first odd number. And then second thing, what I'm doing is last A of I such that we have parity of A of I is not equal to the parity of the last element. Okay, so this is basically finding the last point where the parity is different from the last element. Then I'm checking my two cases. If they sum to an even number, I just print 0. If they sum to an odd number, the first and the last, that means I need to do some operations. And so what I do is either I need to delete numbers till I can reach my opposite parity from the first element, or I need to delete some numbers from the back until I reach opposite parity from the last element. So I'm just taking minimum of those cases and printing. Write this code much more shorter, and because of the contest pressure, I wrote a longer code than required, but this is one way to solve it. There are many other ways, I suppose. Okay, is that fine? Let's move on to B. A was tricky, lost a lot of time on it. A, to be honest, A was actually kind of easy, but yeah, I also wasted like 7 minutes on A, so I can't say much, but yes. Okay, B. We're starting with B now. Okay, time complexity of A, it should be n log n by sorting, and that's the only thing we do. N log n plus everything is O of n, otherwise O of n or constant. So the time complexity for this should be n log n. All right. Now we're going to start with B. Cool. Okay. Yeah, let's go read B. It has system testing finished yet. Okay, not finished, but good to see I did not fail any system tests. Okay, so for B, I also kind of messed up a little bit, but B has a very straightforward solution. If you know bracket questions, if you know basic tricks for bracket questions, it's a very straightforward question. And basically is defining a balanced bracket sequence. Now we will not see their definition of balanced bracket sequence because it is it's defining very formally in grammar and all. So I'll just explain what balanced bracket sequence is. A balanced bracket sequence, let's call it a balanced bracket sequence, or BAL for short, is something, you know, we all do coding, so we know what it means for opening brackets, closing brackets to be, you know, put properly. So a balanced bracket sequence is, this where every opening bracket, every closing bracket has a corresponding opening bracket which comes before it. So that's a balanced bracket sequence in simple terms. Okay. So now you are head of department for combating balanced bracket sequence, and your task is to determine which brackets you can destroy and which brackets you cannot destroy. Okay. So we can remove, your operation you can do is remove exactly one opening bracket and exactly one closing bracket from the string. And your task is to determine whether you can delete two such brackets so that the string is no longer a balanced bracket sequence. Okay. Let us check what is the size of the string. So the size of the string is 10 power 5 over here. So obviously we need an O of n or n log n solution at most. Here are some examples. So let's consider one of the examples. Let's consider a no case first. Or yeah, let's consider a yes case first. Okay, let's take this case. Example of what we want. So what we want to do is basically delete like two brackets, and the first bracket we delete. So we can remove one opening bracket and one closing bracket. So we can delete one opening bracket, one closing bracket, and we have to make it unbalanced somehow. Let's take an example. Let's take the one they gave or something similar to that. So if we have a balance sequence like bracket sequence like this, are there two brackets we can remove, one opening and one closing, so that it becomes unbalanced? And the answer is yes. Yes, there is. If we remove this bracket and we remove this bracket, what happens to the sequence? The sequence becomes like this. But we can see that this closing bracket does not have any opening bracket before it. So therefore, this is not a valid balance sequence. And so the answer for this is yes. But note that not any removal will give us this. If we do some naive removal, in that case, if we do any naive removal, we will not, we might still get a balanced bracket sequence. For example, if we just deleted these two, if we were to delete these two, then it would still remain balanced bracket sequence because as you can see, this thing is still balanced bracket sequence. So this specific cut of these two values is creating an unbalanced bracket sequence. So we need to know how to exactly cut so that maybe there's Kesar Patel says there are stack solutions. Yeah, maybe there are stack solutions, but the solution I'm explaining to you is going to be a very general technique which will help you in all sorts of balance bracket questions, including DP questions or any questions. So pay attention. So yeah. So now that we understood the question, let's see how to think about it. And this is a concept I'll teach you, or maybe you already know, but just take my word for it. And I'm going to define what is known as a balance factor. Balance factor or balance value also sometimes. So we're going to define what is a balance factor for a bracket sequence. So let's take a given bracket sequence, opening, 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 closing, closing, opening, closing, closing. Now, what do we define as balance factor? We define balance factor, let's call it bal of I, bal of I equals number of opening brackets in 0 to I. So in this prefix 0 to I, or if we're writing one index, we can write prefix 1 to I also, minus number of closing brackets, in 1 to I. So in many bracket problems, you can solve it very easily if you think about the balance factor, and this one is no different. So what does this mean practically? So what this means is, for this given string, bracket string, let me write the balance factors. So for first balance factor of the first element, it is simply number of openings minus number of closings. So it's 1. For the first two, now there are 2 openings and no closings. The balance factor here is 2. Now for the first 3, there are 3 openings and no closings. So the balance factor is 3. And then so on. We can go like this, and we can write down the balance factor. So for the first 4, now there's a closing. So it's plus 3 minus 1. So our balance factor will become 2. Then till here, our balance factor becomes 1 because there's now another closing bracket. So it's going to subtract 1 from our answer. Then here it's going to become 2 again. Here it's going to become 1 again. And then in the end, it will be 0 because number of openings equals number of closings by the end of a balanced bracket sequence. So now the interesting thing you see about these is, right? Now, first of all, this array we got, which is our balance factor array, we'll call this balance factor array. In this array, all the numbers are greater than or equal to 0. Val of I is always greater than or equal to 0. And this holds true for any balanced sequence of brackets. If balanced sequence. So for all I, this value, this statement will hold true that its balance factor will be greater than or equal to 0. And if it's unbalanced, then at some point it will become less than 0. And this is a thing which you should know, like if you have done enough problems, you would know this idea already. But I can give you a intuition for why this is true. It is true because if you see the definition of balance of I, it is number of opening minus number of closing. So if it's greater than 0, or greater than equal to 0, it means the number of openings till now has been greater than number of closing. So even if I get a closing bracket over here, there will be some opening bracket it matches with, so it will still remain balanced. But as soon as it becomes negative, we know that our balance, it has become unbalanced because now we have a closing bracket more than opening brackets. And at no point we can have more closing brackets than opening brackets because like a closing can only come after an opening bracket. So let me just give you an example of an unbalanced array. For example, we have something like open, open, close, close. And then we have like a close open. So here it closed before anything opening. So if we write the balance array for this, we get 1, 2, 1, 0, and -1. And why did we get this -1? It's because we got a closing bracket before an opening bracket. And then, of course, the second condition for it to be balanced is that last value should be 0. That just means that number of opening is equal to number of closing. Okay, I hope everyone understood balance factor idea. So now what we're going to do is we're going to use the balance factor idea to make sure that we can, you know, we can make our given string unbalanced or not. So our given string, let's say our given string, let us take the example. So let's take one from their examples here. So, okay, so let's draw this string. Okay. Now let us quickly write the balance factor for all of these. We have 1, 2, 3, sorry, 1, 2, 3, 1, 0. Then again 1, 2, 1, 0. Okay. Here, the interesting part is if we, you should wait, this thing looks unaligned. So this closing corresponds to this. All right. So the interesting idea is we need to make it unbalanced. So we need to make one of these values. We need to make one of these values. We need to make one of these values less than 0. And how can we make one of these values less than 0? The only way we can do this is if we have a closing bracket, right? If we have a closing bracket such that, no, wait, the only way we can make this less than 0 is if we have, let's say, if we have a value of 0 in the middle of the array, right? If we have a value of 0 in the middle of the array, and there is still some brackets left here, and there's some brackets here. So we got a value of 0. If we remove an opening bracket, over here, then we know that this is number of opening minus number of closing. So if we remove an opening bracket before the point where it is 0, and we remove a closing bracket afterwards, we can remove any closing bracket afterwards, it does not matter. So if we can remove an opening bracket before this, that means that it has become unbalanced, because now the value will become -1, because one opening bracket was removed, but closing brackets have stayed the same. So our balance has become -1. So basically the question has become, observe this. So here's the idea, main core idea. The question has become, is there element for which the balance factor, balance of I, is 0, and it is not last element. First element, yeah, it cannot be first element also, but the thing about first element is always be an opening bracket. Otherwise, it won't be a valid bracket sequence itself. And we know the input is a valid bracket sequence. And why is this true? Well, simply look at this balance array, or I can redraw a balance array. Let's say we have some balance array with some positive values and some positive values on this side as well, right? If we have a 0 somewhere in the middle, we can remove the first bracket. We know that the first bracket will always be open, and we can always remove the last bracket. We know the last bracket will always be closing. And what will happen, because we remove this first bracket over here, the balance over here becomes unbalanced. Basically, number of opening and number of closing were equal over here because it was 0. Number of opening minus number of closing was 0. But now number of opening has become 1 less. So number of opening has become -1. So that means at some point our balance factor became -1. And that is the core idea of our algorithm. So is that clear? If we get a opening after closing. No, it's not necessary that an opening after closing will always disturb the balance. Okay. So yeah, I guess you can use stack as well, but I found this simpler so everyone can have their own taste. So how to code this up? So code for this is simple. Create balance array. So balance array is very simple. If you see an opening bracket plus plus, if you see a closing bracket minus minus. So, or you don't even need to create balance array. You can just store the value in a variable. So you can track balance factor basically. Track balance factor, track balance factor. If balance factor is 0, if balance factor is 0 and it is not the last element, so it is, and I is less than n minus 1, so it's not the last element, then yes, we can do it. Else, no. Else we cannot make it unbalanced because 0 never occurs any point in the middle. We can never decrease it to -1 at any point. So basically, we have to decrease it to -1 at any point if you think in terms of the balance factors. And that's only possible if there's a 0 somewhere in the middle. Let's go through the code once. So I input my string. So here I do not know why I used a map. It was not needed. I think it was a previous version of the code. Anyways, so just if you see that submission, just remove the map. There was no reason for it. I was thinking of some other idea. Okay. So n is the size of the string. V is my balance factor. So this is my balance factor. Okay. And answer just holds yes or no. So here I update my balance factor. If I see an opening bracket, I increase the balance factor. If I see a closing bracket, I decrease it. If I equals 0, greater than 0, this is not also required because I will never be 0. The balance factor will never be 0 at I equals 0. So if the balance factor is 0 and I is less than n minus 1, I can say my answer is true and I can see out yes. Otherwise, I see out no. So I hope this was clear. Time complexity will obviously be O of n because we're not doing anything. Memory complexity will also be O of 1 only because there's no new memory being used also here. So time complexity is simply O of n. It always feels nice to solve something in O of n, I guess. O of n. Okay. Right, yeah, you can. This also seems very clever. Ayush says remove first and last element and check if it is a valid parenthesis or not. And true, that's also a valid way to check it. Clearly, from this whole argument, that also becomes obvious because always we can remove first and last and we can check if it becomes valid or not. Okay, let's move on to C now. This is where it gets interesting. C took me some time, although I feel like D was much more of a standard problem. Uh, in terms of rating, for C also we can use stack. I have no clue if you can use stack for C. In terms of, okay, C was also somewhat standard, but the implementation was a bit tricky. So I can understand if people got stuck on it. Okay, let's read C. Okay. You have a drone and you want to win a drone like obstacle competition. Okay. There are n obstacles and the ith obstacle is defined by two numbers, L of I, R of I. Let the height of your drone at the ith obstacle be h of I. Then the drone passes this obstacle if and only if you're between some range, like you're between L of I or R of I, like you're in between this interval. Okay, initially the drone is on the ground, means its height is 0. The flight is represented by arrays D1, D2, till Dn, where D1 is the difference between heights. That means that if your current height at h of I minus 1 was x, then at h of I, it will be h of I minus 1 plus x. So it's like a difference array. If any of you have studied it, it's like the difference array for heights. Okay. And it's also given that d of I is either 0 or 1. So it's 0 less than equal to d of I less than equal to 1. So either your drone will stay at the same height, or at most it will increase height by 1. Okay. So yeah, and you know some values of d of I. So in your plan, you have a plan in which you know some values of d of I, but the rest are marked as minus 1. Replace the unknown d of I with numbers 0 and 1 to create a flight program that passes through the entire obstacle course or report that it's impossible. Okay, we'll see an example soon. Let us check the constraints. So n goes up to 2 times 10 power 5, and then uh, there are some integers d1 till dn, in which if it's minus 1, it means we don't know. It can be 0 or 1. If it's 0, it means we stay at the same level. If it's 1, it means we increase our height by 1. Our initial height is 0, by the way, it's already given. And then there are these obstacles, which are Li, Ri, which means my height at this position should be between Li and Ri to pass to the next position. And I need to see if I can reach the last position. So in this, what we'll do is we need to keep track of basically interval overlaps. So if you have studied interval overlaps, first we'll discuss a concept. So at least this time the contest, unlike last time, was not so ad hoc. They're like known techniques each time. Here is the balance sequence, or you could say stack. First one is obviously number theory, and then the C problem is interval overlaps. So if we have two intervals, okay. So this is theory, I guess. I can call this theory. If I have two intervals and it is L1, R1, L2, and R2. Okay. If I have these two intervals, then which are the overlapping points of these intervals? Well, we can see that the overlapping points are this subinterval, which is here, which we can say L2, R1. And what we can see here is that the overlapping interval between two given intervals is max of L1 and L2, comma, min of R1 and R2. All right. So this is how we find the overlap for two intervals. And additionally, if this is like, if here this R value which we're getting, if it is lesser than the L value which we are getting, then it's not possible and they're non-overlapping. So for example, if we had two non-overlapping and we had L1, R1, L2, R2, then here the minimum of R1 and R2 is this, and maximum of L1 and L2 is this. And we can see that since this is bigger than this, there is no overlap. There is no overlap. So this is one theory we should know before getting into this question. Okay. So what we are going to do, observation one is we will possible range of maintain interval of possible range of heights of your drone, of possible heights of your drone. So let's call this maintain interval of possible heights. Okay. What do I mean by this? It will become clear very soon. Um, okay, so let us take this example. For now, let us not care about d values. Let's just assume that all d values were -1, all were question marks, like we don't know any of the d values, and we'll just see these intervals. Okay, so we are given interval 0, comma 4. So that means at 1, let's draw 1, 2, 3, 4, and let's say this is 0, and let's draw the valid heights. So the valid region here is 0, comma 4. So that means let's say this is 0, this is 4, and if your drone is within this range, then and only then it can fly forward. Okay. And what is the next valid at 2? At 2, the valid is from 1 to 2. So from 1 to 2. All right. And then the valid interval here is from 2 to 4, and then from 1 to 4. So from 2 to 4, from 1 to 4. Okay. So let us see what it means by maintain interval of possible heights. So it is given that in the start, our height is exactly 0. So let's say our current possible height is, let's call the interval as PL and PR. Okay. So this is the smallest possible height and PR is the largest possible height. Again, PL is the smallest possible height we can have and PR will be the largest possible height we can have. In the start, PL and PR will be 0 because we are starting at height of 0. So our only possible height is 0. Now here, we can increase our height by 1 or we can keep our height 0, assuming it's a -1. For now, everything is -1. Our array of D is all -1. Our D array is all -1. So here we can increase our height by 1 or keep it the same height. So that's like our possible heights have become 0 or 1. So this is our possible heights, 0 or 1. And then next step again, we can increase it from 0 to 2. So you get our idea, like every time we can move 1 up, right? So our possible heights either is like we're remaining the same or we're increasing by 1. So those are our possible heights. Now, how does this help us? How this helps us is here our possible heights and the current valid range, which is 0 to 4, we will take the overlap. So between this range, the range in green, the range in green over here, between this range and this range, we'll take the overlap, and this will become basically our valid region. So here the overlap is whole 0 to 1 only, so there's not much point, but that's what our valid region of heights is. Now when we go here to the next stage, again, now our possible heights become 0 to 2, but our valid range is 1 to 2. So the overlap will become again 1 to 2. And this is our possible heights at this stage. So this orange one, these orange colors are all the possible heights we can actually be realistically as a drone. There is some path that keeps us in this range of heights. Okay. So now over here, since our range was 1 to 2, that means our next range can be from 1 to 3, because either we stayed at 1, we stayed at 2, or we increased one step higher in a height from 2. So now our new range is 1 to 3. Now again we do the overlap between these two. We do the overlap between these two, and what do we get? We get our possible heights is between 2 and 3. And this is a very, I guess, subtle idea. Like if you have not seen this before, it might not be that easy to understand. But if you have seen this before, it should be very obvious. The idea basically is we have some possible range. Each time we go to the next step, our possible range, the right value increases by 1. And then we do overlap with our valid values, and we get a new possible range. So now at this step, the possible numbers of heights are 3 and 2. This is the possible range of heights. Now at the end, again, the possible range increases by 1. So it becomes 4 to 2. Again, we do an overlap between 4 and 2 and all the valid ranges here, 4 and 1. And what do we get? Our final answer becomes possible valid heights in the end are 4 to 2. I hope this was understandable, even though the diagram is a bit weird. Or can someone tell in the chat if if they didn't understand? So what I'm doing is, uh, initially our possible range is 0, 0. Initially, initially our possible range, let's just call it something like this, is 0, 0. Then for every I, for every ith obstacle, what do we do? First, we increase our possible range R value by 1. So if my possible range was xy, if my possible range was xy, or LR, if my possible range was LR, then I will make this into L plus 1. Sorry, not L plus 1. L will remain the same because we can stay at the same height, but we can go to R plus 1 height now. So this will become my new possible range. And then again, I will update my possible range equal to overlap between my valid, overlap between my possible range and my obstacle's valid range. So obstacle range. Let's call that obstacle range, or let's just call it obstacle of I. Please understand that this means that we are taking the overlap between the current possible range and the obstacle's possible ranges. What does this mean? We're using this obstacle overlap idea that, max L1, L2, comma min R1, R2, and we're figuring out what is the possible range. So if this range is empty, if it's empty, then we can just print -1 and we know that it's not possible. At any point, if this possible ranges become -1, like there's no possible position, no possible height our drone could have been, then the answer is simply -1. Otherwise, we keep going until all the obstacles are done. Once all the obstacles are done, okay, so once all the obstacles are done and we have some final range, we get final range. So if all the obstacles are done and we did not get a -1 case, we'll get a final range. And these are the final heights, all are valid heights that your drone can be at the end. So let's call this H of L, H of R, which is the range of your valid heights. Okay. Now, one thing which I missed, very important thing, is that this condition, this will only happen if d of I is -1. Like we assumed all of it will be -1, but in the actual question, it will be -1. So if d of I is -1, then and only then we can increase our range to LR plus 1. If d of I is 1, if d of I is 0, then we can't change the values. So the range will become, it will stay LR, the range will stay LR. And if d of I is 1, then the range must become L plus 1, R plus 1. Because you can't stay at L if d of I is 1, you must increase it. Similarly, at any point, you must increase it. So our range becomes L plus 1, R plus 1. And here, what does our range become? It becomes LR plus 1. And yeah, so this step, please uh, based on d of I. So it will be based on d of I. Based on, we'll do different things. So please be wary about this step. Okay. So initially, let's just recap. Okay. Initially, a possible range is 0 to 0. Then for the ith obstacle, if we know that d of I has a fixed value. D of I is 0 or d of I is 1. That means whatever possible range of heights we had, it needs to be shifted accordingly. So if it was 0, the same range of heights will continue. Otherwise, the range of heights will increase by 1 for sure. And if it was not, if it is unknown, then it can be either 0 or 1. So we increase it to LR plus 1 because if we want, we can choose to increase our drone's height. If we don't want, we can choose to not increase our drone's height. So it's L comma R plus 1. Then we do overlap at this obstacle. So we make sure that the obstacle's possible range and our possible range of heights are overlapping. If this becomes empty, we print -1. Otherwise, we get a final range, H of L, H of R, which is our final ending height, which is the possible ending heights. And let's name this solution, like this is almost the final solution. And now for the last and final step, we can backtrack. Since we already know the possible ranges. Since we already know the possible ranges, we can backtrack and find valid d of I. Basically what we want is we need to fill all the values where it is unknown, right? We need to fill the -1 values. So find d of I values. Okay. Now I think up till now it should be like understandable, hopefully. Guys, no bullying on the chat, guys. Okay. All right. So we backtrack on the possible ranges, find d of I values. How do we find d of I values? Okay. So first let's just go through the code for the first part, just to make it clear what we're doing. We take in n, we take in the values of d of I. We'll just input that. Then I'm defining two vectors, range and valid range. We'll see what they do. So range is simply the ranges for the obstacles. So it's going to contain our ranges like it's going to contain our ranges like 0 to 4, 1 to 2. So for each obstacle, you must be between these heights. So that's what range will contain. Then this is the code which I explained right now. The code for the part I explained right now. In fact, let's just take it on. Let's just take it on the draw board. Okay. So this is the code for what I explained so far. Yeah. So basically, we're setting a flag variable possible to true. That means it is possible to create because at the end, if possible is false, then we can print -1 and go to the next test case. Here we have L and R, which is our initial possible range. Like we know that our possible heights initially is 0, 0 because we're starting at 0. So this is basically our possible L, possible R, what we talked about it. Okay. So now what we do is if d of I was 1, then we increase to L plus 1, R plus 1. We know that because if d of I was 1, that means necessarily if our possible range was LR, now our possible range is L plus 1, R plus 1. If d of I is -1, we don't know whether we can choose either to, increase one step or not increase. So our range becomes L, comma, R plus 1. So that is the logic implemented here. If d of I is 0, we don't need to do anything. We can keep with the same range. So update my range, update L of R. So this is what we did here. Now I need to check for overlap. So what my NL and NR are, is this is the overlap of LR, with obstacle. So I'm overlapping with the obstacle, that is the range I dot first, range I dot second with obstacle. And if I see that there's no overlap, then I can just set possible equals false and break and get out of the loop. Otherwise, I will update my LNR to these new values of NNR. NL means just new L, new R, which means the overlap between the obstacle and this. So I'll update the value of LNR and also store in my vector valid ranges. So I'm storing which range is valid at which step. Why am I storing this? Because so we can backtrack. This is for the backtracking step. So I'm going to store this valid range and I'm going to continue. So if it is not possible, print -1. Otherwise, there'll be some LNR. And then in the end, we have that LNR and we can backtrack on it. Now the question is how to backtrack. And that is slightly tricky, I guess, at least in this approach. How to backtrack. Okay. So the way I did it in contest was a little bit messy, but I'll try to explain in a simple way. Okay. Yeah. So basically what I'm going to do is I know that at the end I have some range of heights which are valid. So I have this range of heights, let's say, which I'll call my HL, which is my minimum height which is valid, and HR, which is my maximum height which is valid. If my drone is anywhere between these heights, it's possible to create a sequence to reach that height. Okay. So since anyone is possible, I will just pick the highest one. Okay. So I'll say assume my drone ended at this position because any of these values my drone can end at our given D of I values and range values. So I'll say assume my drone is at this position. My drone is here. Okay. Then I will see the previous interval. I will see the previous interval. And based on that, I'll decide if my drone needs to go down one step or if my drone needs to stay on the same level. Okay. And one more thing, if D of I is 0 or D of I is 1, let's write this in some other ink. If D of I is 0 and D of I is 1, in these cases, we don't need to do anything. We already know the value at that point. So we just update our position. So if D of I was 1, we'll just do position minus minus when going to the next step. And that's all. If D of I was 0, we'll do nothing to position and we'll just go to next step. If D of I was -1, so this is the D of I equals -1 case. So we don't know which one to do, right? So in this, if it is still possible to stay at the same height, I'll stay at the same height. Okay. Because I know the valid ranges at every step. I know that this range is valid at this step and this range is valid at this step and stuff. So since I've already computed that in the first three steps, right? And I know that these are definitely valid range. So if it is possible to stay at the same height, I'll stay at the same height. Otherwise, let's say it was like this. My next range was one value down. Otherwise, I will go one value down and I'll mark D of I as 1. So I'll change D of I's value as 1. Or otherwise, I can have another vector to record my answer. So I'll change that to 1. Otherwise, I will keep D of I as 0 if I'm staying at the same height. So this is how we're going to backtrack. If D of I is already set, we don't need to do anything. If D of I equals -1, we'll see if my current possible range, if I can just keep my same value at the current position, I'm fine. Otherwise, I'll decrease my position and I'll mark D of I equals 1. At the very end, we need to check overlap with 0, 0 as well. So at the last range, we'll get 0, 0. So for that also, we might need to handle, depending on how you store your vectors, you might need to handle separately. Now, because I was in a rush, I did it a bit messily, but let's go through the code together. Uh, at first, is this understandable? Yeah, we can backtrack. Look, guys, I'm not talking about backtrack as in like recursion backtrack. There's no recursion here. I'm just talking that once we have calculated our valid ranges, I am going backwards and calculating my path. So it's not backtracking in recursion sense. It's just backtracking in the sense that I've calculated my valid ranges and I'm going back. So everything is O of n, guys. This is still O of n because it's still a single loop from n-1 to 1. As you can see, it's still a loop from n-1 to I greater than 0, which is 1. Okay. So I'm going to make a deck. Why did I make a deck? Because I wanted to push to front. I didn't want to reverse my vector. So like obviously you can do with a vector also. Let's not question it too much. Um, okay. So int pos, this is my position. All right, it's my current position. And I'm going to set it to my top value of my last valid range. What does that mean? I'm setting it to top value of my last valid range. So go up back to this example. This is our last valid range, right? So I'm setting it to 4 basically. This is the maximum height I can be in a valid sequence of D values. My drone can reach this height maximum. Why maximum? Like it makes the logic easier, that's all. No specific reason. Okay. So for I from n minus 1 to I greater than 0, if the DFY value is already set, then I can simply push front in my deck because I'm doing backtracking, right? So I'm doing it in reverse. So I'm pushing front instead to my deck. So I'm just going to push the value of DFI into my answer. If DFI was 1, because that means that there was a height decrease which happened, or here, see, when you're backtracking, it will be a height decrease. But actually, what is happening is a height increase when you're doing it from front to back, right? From back to front, it'll look like a height decrease. So that's why if DFI is 1, I will decrease my position because that means I came from a lower position. And I'll continue. Otherwise, if if this current position, is still a valid range for the previous value, if the current position is still a valid range for the previous value, then I can simply push back 0. That means I can still stay at the same height. So while I'm backtracking, I can still stay at the same height, no problem. Otherwise, if the valid range has changed, at most the valid range would have changed by 1. Because if the valid range had changed by 2, then this would not be a possible position itself. So at most the valid range would have changed by 1. I know that. So if the valid range has changed, I know that I need to decrease by 1. So I push back 1 to my answer, push front 1 to my answer, and then I decrement my position. Okay. Now this is an exception for the first value, for first value D of 0. So depending on how you make your vectors or arrays, you don't need to write a special exception for this. But we know that the first value, the very first value, it will overlap with 0, 0. And because I had not added 0, 0 to my vector, I'm checking for that overlap specifically. So if D of 0 has been set, we can just push back D of 0. Otherwise, we will check if the current position is 0, in which case we'll push back 0. Otherwise, if the position is 1, we know that we need to decrease it. So we'll push back 1. So that's it. And then after this, we can just print out the answer. So let's go through all of this for a minute. Like if it seems complicated, just remember this, that the idea of overlapping intervals and increasing intervals come up so often that thinking of it this way, in this general kind of way, will help you in a lot of questions because many questions use similar ideas. Okay, so what did we discuss? Let's just recap. We discussed when two intervals are overlapping and how to find the if two intervals are overlapping. Then we discussed that in our start, we'll maintain an interval of the possible heights we are at. At I equals 0, our possible heights are 0, 0, that interval. And then each time, if it's a minus 1, if it's a minus 1, that means we can increase the R value by 1. If it's a 0, then L and R will stay the same. And if it's a 1, that means L plus 1, R plus 1 will be our new range of possible heights. All right. And then we'll check overlap with the current valid points. Current valid points as in the the given obstacles valid points. And those are our final valid points for this obstacle, ith obstacle. So again, yeah. So initially our possible range is 0, 0. For the ith obstacle, we update it using these formulas. Then if the overlap point is empty at any point, we call it -1. Otherwise, we have a final range. Also, while doing this, we will store all the valid ranges in a vector called valid range. Why are we doing this? We're storing in valid range because we want to use it later for backtracking. Later, we will backtrack on the possible ranges and find the correct DFI value. How will we do this? What we're going to do is basically last value is always valid. So we can say that last value always valid. What do I mean by last value? That means in my final range HL HR, we know that HR is a valid value, right? So we'll just start at HR. We'll say our drone was at this height HR, and then we'll look at the previous range and we'll see if we need to uh, if we can stay at the same level or if we need to decrease the level. Every time we're not sure, every time D of I is -1, we can just check if we need to decrease the level or stay at the same level. And that's it. Once we have done that, this could be written much cleaner, but I did it in contest time. So once we're done with this, we can simply print out the answer. Uh, let me just give what can be the rating of C? We can start with HL. We can start with HL. Definitely, we can start with HL. If we start with HL though, what we need to do is we need to again keep track if this is overlapping. If it ever overlaps, we need to go down. Okay, yeah, we can pretty much do the exact same thing. So yeah, we can start with HL or HR. It does not matter. Yeah. So that should answer your query. Yeah, we can start with back minimum, Chirag. We can. I think the logic will remain pretty much the same. For me, back maximum was more intuitive during the contest. That's the only reason I wrote it that way. What can be the rating of C? I think the rating should be like there were a lot of solves and it's kind of a standard idea. So I guess is my best guess is like 1300 to 1400. I am sure maybe my method, although it's very general, maybe like there's a slightly easier way to think about it, which is why there are so many solves. So I'm not sure about it. So yeah, this will be the expected rating, I guess. And for D, I suppose it'll be 1700, 1800. Okay. So should we move on to D? Problem D. Okay, let's discuss time complexity. We forgot. So there is no sorting here, and we're just going through all the ranges. Again, this is O of n, this is O of n. So for C, the time complexity is O of n. So I'll just write this. Okay. Now we can do problem D. Is that fine? Let's move on to problem D. Unless someone has like some specific doubt for C. I think a lot of you were waiting for problem D itself. Okay. Okay, we'll just I have no clue what that was, but all right. So I'll just wait a minute in case anyone has any doubts. If you put it on the chat, uh, I'll go drink some water till then, and then we'll start problem D. All right. Fewer batteries. So the problem statement itself is very complicated. I'll explain it in a simple way after reading it. There are n checkpoints, and the ith checkpoint contains B of I batteries. Initially, robot starts at first checkpoint with no batteries, and it must reach the nth checkpoint. Okay, so there's a robot. It's starting at some first checkpoint, and it must reach the nth checkpoint. There are a total of m one-way passages between the checkpoints. All right. And the ith passage allows movement from S of I to T of I, but not the other way. Okay, so it's like a graph with edges, but the edges are directed. So we can only go front. And see, we can see S of I less than T of I. So that means if we have n passages, let us just draw them. So clearly already it's a graph problem. So each checkpoint is like a node, and then the passage is like edges. So we immediately got that, I guess. 5, 6. So here my n equals 6. Okay. my n equals 6, and I drew my graph. And then what it's saying is we have one-way passage, so directed graph, and it goes from S of I to T of I. So we can have stuff like this, basically. But it can never go backwards. It will not go backwards because it is given here that S of I is less than T of I. So we have some graph like this. Let's read more. Okay. When a robot arrives at point V, it can additionally take any number of batteries from 0 to B of V. Okay. So we already know that ith checkpoint contains B of I batteries. So this is like the value or weight or something given to each node. So let's just write something like B1, B2, B3, B4. So these are the batteries at each of these nodes. B5, B6. Okay. So these are the batteries at each of these nodes. And we can take any number of batteries. So basically, these are like batteries they're kept on a shelf or something. And if we want, we can take it. If we don't want, we cannot take it. It's up to us, and we can move on. Okay, so it recharges all previously collected batteries at a checkpoint. So whatever batteries we have so far, let's say in a bag or something, imagine we have the robot and we have all the batteries in a bag. We can recharge all of them. At any point, all the batteries are recharged. Okay, right. And one thing we forgot to mention, the ith passage can only be used if the robot has at least W of I charge batteries. So each passage, so it's a weighted directed graph, and each passage has a weight of W of I. Otherwise, if it does not have, W of I charged batteries, it'll run out of power. So what does that look like? That looks like we have some, W of I, some weight over here. So that means that we need at least this much battery. Like let's say if this is 3, and over here if B of 1 was only 2, right? So we not have enough batteries to go across. So that's what it means. So let's just put some random numbers here. So this requires 7 charge batteries. This requires 6 charge batteries. Okay. So what is the constraints? N is 10 power 5, usual for graph problems. Wait, sorry, wrong problem. But yeah, N is still 10 power 5. Okay. Usual for graph problems. M is also roughly 10 power 5. So that's the number of passages or number of edges in this directed graph. Then we're given B of I, which is the value of each node. Then we're given the S of I, T of I, which means starting point of this directed edge, ending point of this directed edge, weight of this directed edge. Weight means the number of batteries required to go through this edge. And yeah, the sum guarantee is there for N and N. Okay. And we also observe that the number of batteries required can go up to 10 power 9. So that's about it. Let's discuss a test case. So to yeah, okay. So let's discuss this test case. Example one, because the question is complicated. Let's see some test case and figure out what it wants exactly. So I'll draw 3 nodes, and we can see that 1 to 2 is connected with weight of 1, 2 to 3 with weight of 1, 1 to 3 with weight of 2. So basically our connections look like this. Yeah. And then how many batteries are available? Here 2 batteries are available. Here 0 batteries are available. Here 0 batteries are available. So observe that this is a very, very trivial case. It does not give us much information about the problem. It's pretty trivial. But so basically we can see that if we have 2 batteries here and we choose both of them, then we can use this edge directly to reach here, or we can go 1 and 1. So with only one battery. And yeah, what does the question want again? The question wants the minimum number of batteries that the robot can have at the end of his journey. So he should reach the last value. He should go from the first to the last, reach with minimum batteries. So maybe you don't want to carry too much in your bag or something. Like imagine you're the robot and you are carrying it in your bag and it's too heavy. So what is the path or the way to reach with minimum batteries to the end? All right. Okay. So here we can see that we can reach with only one battery. Here we have the option of picking two batteries, but we'll only pick one battery. Then we can charge it, go here. And then again, we'll recharge that one battery and go here. Right? So that makes sense. So let's think about how to solve this. So the first observation, or in fact, 0th observation, because it's a very simple observation. Observation number 0. And that observation is charge of the battery does not matter. Like whether it's charged, like all batteries can be charged, right? So charge doesn't matter to the question. I don't know why they added it. Doesn't matter. All it matters is how many battery I have. So we don't need to think about charge. Don't need to complicate the problem. All it matters is till now how many battery I have. Only sum of batteries taken. Let's say we chose some B of, or maybe like X batteries at each turn. So X of my I, and if I've taken some path P, so sum of batteries, sum of number of batteries taken. Okay. Now, interestingly, this question is pretty not that straightforward because first of all, we need to reach the end of the journey, but at the same time, we need to use minimum number of batteries. All right. So what does this mean? Because since we know that if we have more batteries, right, later in our path it will help us. So let's call this intuition. Intuition. Like if every time we took as many batteries as we could, right, it would be better for us to reach the end because more batteries is better for us. More batteries is better for us because we can cross more edges because it'll help us cross more edges. Help cross more edges. But again, the question is asking like there are like two competing forces. One, we want to take as many batteries as possible so we can cross as much. But then the question is asking us for minimum again. So it wants to find the minimum number of batteries and which still wants us to, reach our endpoint, which is node n. So how do we make sense of these two conflicting desires? So I'll teach you one good technique when thinking about problems where there's a conflicting desire. This desire to have more batteries so that we can cross more edges versus this desire to take the minimum number of batteries. What if we took two less batteries and later in our path we could not cross some edge? So how do we deal with this? We just ignore one of them for now. We'll use this idea which is known as wishful thinking. We'll assume that, just more batteries is better. We'll forget about this. We'll think about only solving for this first. Then once we're satisfied with it, then we'll think about both the cases. Okay. So now let's see if we could store as many batteries as possible, right? How would we find out that can we reach the end or not? Well, it's simple. At every node, so let's do Let's just write wishful thinking. And why am I telling you this? Because, it's also called relaxing the constraints of your problem. And it's a very useful mental trick. A lot of you people ask, right, how do you come up with these ideas during contest? So that's why I'm explaining the thinking process behind this. Visual thinking, let's just consider more batteries as better and think what happens. What happens if we take more batteries and we try to reach the end? At least we'll find out if it's possible or not, right? At least we'll do that. Let's not deal with both of these things at the same time. Let's think about more batteries. Okay, so basically, what this means is since every path goes only forward, like if I'm at this node, that means my edges will only come from nodes from the back. My edges cannot come from nodes from the front because that's how the question is stated. So let's say that the maximum batteries I could have here was some X, and the maximum batteries I could have here was some Y. And if my weights were enough, like if X was bigger than this weight, and if Y was bigger than this weight W2, right? And I can reach here, then how many batteries will I have here? I will have max of XY. What is the maximum number of batteries I can have here? It will be max of XY plus plus the number of batteries which I can take from here also. So let's say that number is, let's say they were like, some B of 3 batteries. So I'll add B of 3 here. So this is the maximum number of batteries I can have at this point. So basically, what will be our algorithm? This will at least figure out whether it's possible or not to reach the end. So we're taking maximum batteries at each time and we're ignoring the minimum battery condition. So what is our algorithm? For I from 0 to n, so for 0, we don't even need to do anything because we're starting over there. From I to 1 to n, or technically 1 to, if it's 0 indexed, it'll be 1 to n minus 1. If it's 1 index, it'll be 2 to n. So let's use 1 index. For I from 2 to n, for my node, I guess you should know at least at this level what in degree out degree is. For all in vertices or in degree vertices, whatever you want to call them, for all in vertices. And this is a kind of DP, I guess. It's a kind of DP on a DAG. Since I've already calculated for each node, I will calculate basically DP of node, DP of I. What is the maximum number of batteries I can reach this node? And if I cannot reach this node, it should be like minus infinity. Max batteries with which I can reach this node at I. Okay. Why am I doing all this? Even if the question does not want max batteries, you'll understand soon enough. Okay. So then for all in vertices, if so all in vertices J, and we know that J is going to be less than I for sure. So for all in vertices J, if J or dP of J is greater than or equal to weight, because otherwise it won't be able to cross that edge only. So if the number of batteries I had at J is greater than or equal to the weight, then I can go from from J to I. If this is true, then my dP of I will be equal to max of dP of I, comma, my uh, using this edge, right? So using this edge, how many batteries I got? I got dP of J batteries plus my own number of batteries which I already have, which is B of I. So this is what our dP will look like. And in the end, if the nth node, if nth node is negativity not possible to reach, it is not possible to reach because we set everything to negative infinity at the start. Not possible. And if the nth node is some value x, let's say it's equal to x, not equal to negative infinity. If nth, by nth I mean dp of n. Okay, dp of n is what I mean by nth value. And if dp of n is some x not equal to infinity, negative infinity, then it's possible, and the maximum batteries we can have till here is dp of n, basically. And so here we using dp we found out what is the maximum battery at each node, basically. And since we know that at some node all the previous nodes are already processed by a dp, so yeah. What were the website which showed details of problem in CF like rating? Okay, so yeah, it's CList, I believe. I believe you're talking about CList. So yeah, cool. Now, what is the next step? Yeah. So now you need some intuition. And our intuition is, look, here we're taking as many batteries as possible, right? But now we need to find the minimum of how many batteries we need to take. So our intuition is going to be, let's call this intuition 2 or observation 2. And this is going to be binary search on minimum. What do I mean by that? Like, how do you think of that? Well, once you understood that, you know, once you understood the logic of this, that you using DP, you can find out the maximum batteries. How can let's think about how to binary search on minimum batteries required. And how can we do that? Like, okay, I understand that if I have some amount of batteries, then if I have a greater amount of batteries, obviously I can still do it. Because if I took a greater amount of batteries, I will still cross all the edges. So we can see that monotonicity is maintained because if I limit my maximum amount of batteries, first let me just write the condition which we're searching for. Max batteries which I can take at any time. Let's say my bag had some capacity, right? Is mid, is my mid of my band research. Okay. And then I will check if possible using that above DP approach. So DP on DAG or Dijkstra or whatever you want. We don't need Dijkstra or top sort or anything because the structure of the graph is so easy. Using Dijkstra is overkill. We can just do it in overfin. I think someone mentioned Dijkstra in the chat. Yeah, Jeet Mehta. Yeah, so we don't need Dijkstra. We can just do it directly because the structure of the graph is, linear. It's already topologically sorted. Okay, so we can. So what we're binary searching on is my max number of batteries less than equal to some mid or not. So we want to find minimum, right? So if I set my max batteries to less than equal to mid or less than equal to X, I want to find out if it's possible with keeping our max batteries less than equal to X. Now, how do we manipulate this DP to make sure that the sum does not ever exceed X? So it's very simple. We don't need to do much, but yeah, we can write it like this. Uh, okay, how does, I guess copy paste doesn't work here. Right. So how do we modify this DP to make sure that the number of batteries we take at any point does not exceed mid or like the value we're binary searching? So what we can do here is instead of this DP just simply going max of DP of I, DP of j plus B of I, here we do a condition. We just put a min over here, like min this value with our value of mid. So let's just write that. Uh, let me erase this. Let's write this out. We can write dphi of I is max dphi of I min of mid, which is the what is mid again? Mid is the like value we're trying. We should never exceed mid, and we should still ensure it's possible or not. And we take min of mid, comma, this value, dp of j plus b of I. And this is how intuitively I thought about it in the contest. Maybe some people would have thought of binary search immediately and gone directly for that. So I first thought about thinking about, thinking about what happens if we just keep getting more batteries. Then it hit me that, oh, okay, if I limit my number of batteries. So the idea is if you limit your number of batteries at some point, if you just keep getting more batteries, but you can use the same technique, but you limit your number of batteries at some point called mid or X or whatever. And then you can binary search over it. So basically it's the same idea, but here, because we're doing this min step, because we're doing this min step, the number of batteries we can ever take total is limited to mid or X or whatever value we're binary searching for. So here it's the same idea but limited. So we can always, it's not maximum battery, it's maximum batteries but limited to less than or equal to mid batteries. And then what we need to check if can we reach the last or the nth node with these number of batteries. So let's go through this like from a binary search point of view also. So what is our final idea? Our idea is binary search on number of batteries required. So BS for binary search on number of batteries required. And what will be the range of this? You can observe that the largest edge is the maximum number of batteries we'll ever require. Because if we have something larger than the largest edge, then it can go through all the other edges. So we never need any more batteries than that. So the range L will be 0, that 0 battery is required, and R will be largest edge plus 1 or something. So I just set R is 10 power 9 or something like this. So I'm going to binary search in this range. And what will I check? Check if it's possible to reach. Check if it's possible to reach. To reach N. To reach nth node. So these are our two steps. And how do we check if it's possible? We do DP, where we take as many nodes as we take as many batteries as we can, less than or equal to mid at each time. At each node. And see if it's possible. So finally we'll check if the last node is equal to negative infinity or has some value. Check last node not equal to negative infinity. And then with this, we can narrow down our binary search and finally done. So yeah, it was if you're good at binary search, this was very simple problem. In fact, I'm not sure what rating they'll give this, but might as well be 1600. I don't think CList will have the rating out yet. Okay, so let's go through the code. I think this is simple. I think I made the explanation complicated. Okay, maybe if you just thought about binary search in the start itself, it would have been easy. But that's not the way I thought about it. And I thought, many people complain like, how do I think of binary search itself? So yeah, Um, let's go through the code. Okay. So first, we take in n and we take in m, which is the number of nodes and the number of edges. So I'm storing nodes, edges, and this vector is my in vector, which means it will hold all the edges coming in at a node, like my in degree of the node, because that's what I care about while doing my DP. So this is nm, and this is my in vector. This is v. V stores my number of batteries, like values at each node. So this v stands for value at each node. Okay. So I'm storing it globally because then I can use it easily in my check function, predicate function, some people call it. Okay. So I'm clearing my vector and resizing it, taking in all the values, clearing my in degree vector, resizing it. I'm taking node STW, so start point, end point with weight for my directed edge. The in degree of the endpoint. Note this, the in degree of the endpoint increases with S and the weight. All right. Okay. So now I do a binary search and very basic binary search code. I have an L and R. I took some extra R just for good luck. And I use this form of binary search. So L less than equal to R. I find mid. You can observe that R plus L by 2 will never overflow for this value of R. That's why I use this formula. Otherwise, of course, you can use L plus R minus L whole divided by 2, which is the better way of doing it. But during the contest, I thought that it will never overflow, and I was right. Okay. So if I then I do check of my middle value. If my current value is sufficient to reach the end, if the current value of batteries is sufficient to reach, I update my best. Otherwise, I do. Now in the very end, if none of the values are possible, R the best will remain R, right? So then I can just if not check best, I can put -1. Otherwise, I see out best. Okay. How does the check function work? So some people said you can use Dijkstra's or you can use the maybe top sort or something like that. But we don't need to use it. Like I explained, we can just do it directly with DP. What we can do is DP of I holds the maximum value of batteries we can have at any node, as I explained. Maximum value of batteries we can have at any node, given that it's less than or equal to sum or mid or whatever you want to call it. So it's less than or equal to the current sum. Okay. So DP of 0 will simply be V of 0, like min of sum comma V of 0. So it's the minimum of the number of batteries at the first node and our mid value. So we're taking the minimum of those two because we never want to exceed our mid value ever. Okay. So then for all I from 1 to n, for all incoming edges to this node, for all j comma w in the incoming edge, if the weight is enough to cross it, that means if this weight of this edge is less than dp of j, so that means we had enough batteries to cross this edge. I update my value of dp, so it becomes uh, the maximum of its current value with this value dp of j plus v of I. So if we took that edge and came here, so we have all the batteries from that way plus the extra batteries we took from this node, and the minimum of that with sum or mid. So minimum of that, minimum of that, minimum of that with sum. So yeah, pretty straightforward code, I think. Like for a D problem, this was pretty standard. So I tried dp in D. Okay. Why W less than equal to dp of J? Where? Right. Okay. Why W less than equal to dp of J? Would lower bound of binary search equal to edge weight be better? Yeah. So if you take the minimum edge weight, you could do that lower bound. Yeah. Why W less than equal to dp of J? So I'll just explain that quickly. Why W is less than equal to dp of J? Okay. So dp of J holds the maximum value I can take to reach some node at some point, right? So like this is the maximum number of batteries I can have at J. Now there's an edge over here. dp of J is my maximum number of batteries I can have at this node. given that my restriction is there. Okay. Now there is this edge of weight W, and that's the way we reach I. Now when we're looking at I, first we need to know if we could cross this edge at all. If we can't cross this edge, then there's no point thinking about it. So when can we cross this edge? We can cross this edge if we have enough batteries, which is greater than W. Therefore, we need dP of J greater than or equal to W. Because at the previous node, if we did not have enough batteries to even cross this edge, there's no point thinking about this edge. Is that clear for Chirag? Yeah. So basically, it's a very straightforward because we know that the edges go from previous to later. That's why we're able to do like one clean sweep DP. Otherwise, we might need to topological sort the graph if that condition was not there and then do it. Here, the graph is already topologically sorted and it's given in the order, so there's no problem. Okay, so that's about it. Let's analyze the time complexity of our solution. Uh, this is basically O of n plus m because for each node and for each like edge, we're considering at most one time. So the check function or predicate function itself is n plus m. Now for binary search, we need to see log of search space. So it gets multiplied to log of search space. So how much is our search space? It's the maximum value of any weight, which is like 10 power 9. So it's going to be log of max wi. So this solution time complexity should be something like this, which is enough for constraints. So roughly operations, number of operations will be something like around this order is a rough approximation. So like 10 to 5 times 6 times, sorry. Yeah, so n, you see the values of the constraints, it should be something like this, which is more than enough operations, like which is like there's more than enough time to do these many operations and figure out the answer, especially when you have 3 seconds. So I think they gave 3 seconds so that if people do Dijkstra's or like they have a log factor, then also they can do it. Ayush Agarwal. So can we solve it like first we found max battery at node n, and then our low will be 0 and our high will be the max battery. And then we can do binary search. Yes, yes, yes. We can just set it to max battery. So here if I in my edges, if I kept a track of max W, like if I had a keep track of max W, then over here I could just set it to max W. So I could set R equals max W here. So max weight of any edge or maximum number of batteries demanded by any edge. So yeah, that's perfectly fine. But it is like it's not needed because it won't change the time complexity much. And mark one to those nodes which are visited. Yeah, we can always mark one to check if the nodes are visited or not. So we can have like another array over here, array for visited. And but yeah, to know that if the node is visited, it needs a again it will need a non-zero DP like like here we set it to negative infinity, right? Minus 1e9 is negative. So to know if it's visited, that means that at least one of the edges were valid. So yeah, we can set visited equals true over here. We can set visited equals true over here. And then we can just check if visited or but then that's wasting an extra array, so I did not want to do it. So yeah, we can do it that way. Okay, I guess that's it for D and that's it for this contest. Again, before ending, I want to remind you that, TLE self-paced course is going on right now. You can go to the website and check it out. It has recorded video lectures for all these topics for binary search, for, it discusses many problems with brackets, sequences like which appeared in this contest. And the balance factor idea also, you will see it at some point while doing the practice problems. There are a lot of practice problems, guided hints, video solutions, and as well as a doubt support. In fact, I am also a doubt support mentor. So uh, for people enrolled in the TLE self-pairs course currently, when they ask doubts, I sometimes answer them. So yeah, yeah. So yeah, thank you everyone. We're going to end the session now. Um, do check out TL Eliminators course. It's also in multiple levels. So at whatever level, whatever rating you are, there's the course for you. I hope today's explanation was understandable and is decent. Today was a pretty easy contest, I think, or at least it's a more normal contest like it used to be a few months ago. Recently, there have been harder contests, I think. So yeah, there's no need to think about the extra when there's easier solutions. All right, thank you everyone. Thank you for watching, and I hope you learned something. Bye bye.